Welcome back to the video course on fluid mechanics. The last lecture we were discussing about the boundary layer and its formation and various theories to analyze the boundary layer for various parameters like velocity variation, shear stress and pressure variation. So, we have seen say starting from the Prandtl's boundary layer equations, we have seen the various solutions with respect to the Blasius solutions and then the momentum integral equations, and then we have derived various equations which we can utilize to analyze the boundary layer, especially for flow over immersed bodies and flow over a flat plate, and also flow through a pipe with respect to the boundary layer formation for the external flows as well as internal flows. Now, in the boundary layer, as far as boundary layer is concerned, one of the important aspect is the separation of the boundary layer. So, we have seen that the boundary layer say when it forms with respect to the flow over external bodies, depending upon the shape of the body, depending upon the fluid properties, the boundary layer thickness can vary, boundary layer thickness can change with respect to the various parameters. So, as far as most of the blunt bodies like a circular cylinder, or depending upon the say a sphere, or depending upon the body shape, the boundary layer can separate. So, now today we will discuss the separation of boundary layer. So, depending upon the case, the boundary layer separates, whether say depending upon the shape of the body, depending upon the fluid flow parameters, the boundary layer can separate say at various locations with respect to the flow. So, here you can see the flow over a sphere is flow over a cylinder is animated here. You can see that the flow is coming here, and then you can see that it is separated at some locations after the some of these locations. So, like this depending upon the problem. So, here I will show another figure. So, here say this video is taken from the book of fluid mechanics by Munson. So, here you can see that this simulates the flow over a cube or a flow over a rectangular block. So, you can see that it is coming here and then separating, the boundary layer is separating after some time. So, depending upon the case, so the flow separation takes place, and then the flow is say at some particular location the flow separation takes place, and then we have to find out in the boundary layer analysis where the flow separation starts and what are the various parameters as far as various properties as with respect to the boundary layer separation. So, when we consider the separation of boundary layer, if flow over a boundary occurs, there are typically three conditions. First condition is case A, where pressure decreases in the direction of flow, the fluid will accelerate and the boundary layer will become thinner. This is called the convergent type of flow. So, you can see that here the flow comes, and then there is a convergence as far as the flow is concerned, and then the from here onwards the dP by dx is less than 0. So, that pressure decreases and the fluid will accelerate and the boundary layer will become thinner in this case. And the second case is case B, where the say if you consider the flow over a flat plate, then you can see that here there is no variation in pressure in the flow direction. So, example flow along a flat plate, velocity gradient is constant. So, here you can see that here the free stream velocity coming, and then the boundary layer is developed, and initially laminar and then transition and turbulent boundary layer. So, here is the second case, there is no pressure variation in the flow direction. And the third case is here the pressure increases in the direction of flow. So, that means here you can see that say here the flow diverges. So, the dP by dx is greater than 0. So, you can see that positive pressure gradient exists, and this kinds of flow is called a divergent flow. So, depending upon case A or case B or case C, whether convergent flow or flow over a flat plate which we consider, or the divergent flow, you can see that the boundary layer say separation or the boundary layer properties changes, and then especially the third case where the last case where we considered the divergent flow, you can see that a reverse flow layer tends to push itself between the wall and boundary layer, and in this way separate it from the wall. This phenomena which separates the boundary layer from the wall or the body is called the separation. So, these three cases I have presented here to show how the variation takes place, and which is the most obvious case where the separation is immediately visible. So, in the case C for the divergent flow, you can see that a reverse flow layer tends to push itself between the wall and the boundary layer, and then separation starts. So, this process, the boundary layer, where the boundary layer separates from the wall or the body, that say phenomena is called boundary layer separation. And then generally this separation location, the location of the boundary layer separation, we can find out. We can find out the velocity gradient del u by del y in the y direction at y is equal to 0. If we equate this to 0, then we can find out the location of the separation point. So, you can see here in the case of this flat plate what is happening, and then divergent flows what is happening we can see. So, with respect to the tip, the say which we have already analyzed with respect to Kc, the divergent flow, very easily visible how the separation, the phenomena of separation takes place, and then we can find out by equating del u by del y is equal to 0, we can find out where the location of the separation point. And then we can draw the separation streamline, and then a wake formation also. So, that means due to the pressure difference here, the pressure changes with respect to the boundary layer formation, and then a wake is formed. So, this separation streamline and wake are two important things in the boundary layer separation which we have to consider. So, while discussing the boundary layer separation, while analyzing the boundary layer separation, we have to find out the separation streamline, and then we have to see that whether any low pressure area or the wake formation takes place behind the body or after the separation takes place. So, this separation and wake formation, say here this slide shows say how the separation point where it starts and then how the process taking place. So, the line of 0 velocity divide the forward flow and backward flow, leaves the boundary surface at the separation point and is known as a separation streamline. So, we can just find out the line of 0 velocity which divide the forward flow and the backward flow, which leaves the boundary surface at the separation point. So, we can find out the streamline, and the region between the separation streamline and the boundary surface is known as wake. So, here you can see that this is the before any say wherever the boundary layer formation takes place, and then any separation starts, the if you plot the velocity it will be in this form, and wherever the separation point starts you can see that it will be going this level, and then you can see that after the separation streamlines forms, you can see that the velocity, the direction of the velocity reverse, and you can see that it will be of this form, so that we can find out the separation streamline. So, we can plot the separation streamline. So, the separation streamline and wake formation, so we have to analyze. When we analyze the boundary layer separation, we have to discuss with respect to the separation streamlines and the wake formation. So, if you consider a cylinder like this, you can see that here the flow over a flow past a spherical or a cylindrical object in 2D, then you can see that the free stream is coming like this, and then here we can say there will be say a location where the flow velocity is 0, so that is called stagnation point. So, here P is the stagnation point, and then you can see that the separation, if you plot the boundary layer, you can see that about this location at Q the boundary layer separation starts. So, we can say that this is the separation point, and then you can see that so here say between the two separating streamlines, you can see that a wake will be formed. So, here in this figure P is the stagnation point, Q is the separation point, and then S is the say where it is located in the wake as far as the flow over a sphere or a cylindrical object in 2 dimension is concerned. So, now as far as separation and wake formation is concerned, so again we can see depending upon various parameters whether the cylinder is smooth or whether the cylinder is rough, you can see that the boundary layer formation as well as the boundary layer separation changes. So, here now with respect to the flow over a cylindrical say flow over a sphere or cylinder in 2 dimension which we have seen in the previous slide. So, here say at R separation already took place. So, here as I mentioned earlier, Q is the separation point, and then there onwards the separation already took place, and then you can see that the wake is formed, and this shows the wake. So, you can see that after this say within this wake there will be clockwise and anti-clockwise vortices will be formed, and then this region is called the wake, and this process is called wake formation as shown in this figure. So, here the free stream is coming like this, and then here is a stagnation point and Q is the separation point, and R is the already separation takes place. Then you can see that the separating streamline is like this, and then this region a wake is formed, and then S is this point, S is in the zone of wake formation, and depending upon the case, depending upon the whether we are considering circular cylinder or whether depending upon the smoothness of the cylinder and then also the fluid properties, we can see that clockwise and anti-clockwise vortices may be formed depending upon the case. So, you can see that this is one clockwise and anti-clockwise vortices are formed within this wake. So, this is what we can generally observe. This we can easily visualize through experiments how this separation and then the wake formation takes place. So, now as I mentioned, say after the separation starts and the separating streamlines also identified, then you can see that at some distance downstream of the body we can visualize a regular pattern of two rows of vortices. So, here with respect to this slide it is very much clear. So, here a sphere is there and then flow takes place. So, then we can see that at some distance downstream of the body we can visualize a regular pattern of two rows of vertices, and these two rows of vertices move alternatively clockwise and anti-clockwise. So, this is called Karman vortex streamline. So, you can see that this is the two-dimensional Karman vortex. So, this depending upon the so here it is plotted for the sphere, or we can also plot it for the circular cylinder. So, depending upon the various flow parameters as well as the nature of the sphere or the cylinder, its smoothness, then we can see that a Karman vortex will be formed. So, we can see that a regular pattern two rows of vortices, which is as you can see that here it starts and then a Karman vortex will be formed with respect to the sphere or cylinder which we consider. So, this is the after effect of the boundary layer separation, and then within the wake and this Karman vortex is formed. So, like this, so this boundary layer separation is very important in the design of many of the automobiles like cars, truck, bus, and also it is very important in the case of say aeroplane design or space shuttle or the rocket design, as far as the depending upon the shape, say the separation may start or earlier or separation will be at the end. So, accordingly the various fluid flow parameters, the velocity, the pressure, etc. will be changing. So, it is very important to analyze where the boundary layer separation starts and then how the wake formation takes place and its properties. So, here now we will just discuss some of the examples of boundary layer separation. So, first case is a divergent duct or diffuser. So, as we have seen earlier, so here the flow is coming like this and then there is a divergent duct, it is diverging like this, or as in the case of a diffuser. So, you can see that here the boundary layer is formed and then the separation starts, and then as the angle increases the probability of boundary layer separation also increases. So, depending upon the case. So, first example here you can see the divergent duct or diffuser. So, the boundary layer depending upon if the angle is more, then you can see the probability of boundary separation also increases. So, this is the divergent duct or diffuser where boundary layer separation takes place. And then second case is a T junction. So, where this is another example where you can see that flow is coming this direction and then it will be going in the direction of B as well as in the direction of C. So, here the pressures at B and C are higher than at A depending upon the case, and there exist two adverse pressure gradients with respect to A. So, you can see that in this case there is a possibility of two zones of separation as far as the boundary layer is concerned. You can see that here this boundary layer will be formed here and then the separation, and here the boundary layer formation and the separation. So, here there are possibility of two zones of separation. So, this is the case of a T junction, and then as we have already seen the third, the case is the flow over a cylinder or a sphere. So, here we consider a ball. So, the free stream flow over a ball, you can see that depending upon the property, the smoothness of the ball, we can have a thick wake or a thin wake. So, here in the case of smooth ball, we can see that the separation starts much earlier. So, you can see the free stream is coming like this, and then here the laminar boundary layer will be somewhere and then transition, and then you can see that the boundary layer separation starts much earlier. So, that at this location the boundary layer separation starts, and the streamline boundary layer, the separative streamline is this one, and then you can see that there will be a thick wake. The reason is that here the ball which we consider is smooth, so we will be having a thick wake as shown in this slide. And then as I mentioned, this depends upon the separation as well as the wake formation depends upon the smoothness of this surface also over which the flow takes place. So, the same ball which we considered in the last slide, if the ball is rough or the sphere is rough, then you can see that the boundary layer separation starts later stage, and then there will be a thin wake. So, this slide shows, so here the free stream velocity and then the laminar boundary layer and then transition, then you can see that there will be a turbulent boundary layer, and here due to the roughness of the ball, say for example in the case of a golf ball or say various other kinds of ball where the surface is rough, you can see that separation is much after. So, here this location is the separation starts, and then you can see that this is the separating streamline. So, in this case the separation is much, say, so here this is smooth ball case where the separation is much earlier, here the separation is much later, the boundary layer separation is much later, and then so that we will be having a thin wake. So that is why I mentioned, so we have to see that not only the flow properties, the fluid properties, but the depending upon the case, say whether the surface is smooth or surface is rough, again the boundary layer, the characteristics will be different, and then the separation also starts earlier or later, and then also the wake formation also it can be thin or thick depending upon the case. So, this is the fourth case where say the flow over a rough ball and then the separation with respect to the rough ball. And then fifth case is the flow past airfoil. So, this airfoil we can use to see the how the separation takes place by placing at different say different angles. So, here you can see that in this slide the flow past an airfoil. So, if you place the free stream is coming like this, and if here this is the airfoil, and then you can see that if the angle of attack is 0. So, you can see that say if the airfoil is perfectly made in such a way that we can have a structure where there is no separation takes place, you can see that the flow is going like this. So, there is no boundary layer separation. So, this is the case for 0 angle of attack, but the same airfoil if you just slightly tilt so that there is some angle is formed, then you can see that say for example 5 degree of angle of attack, then you can see that the boundary layer will be totally of different nature, and then the separation flow separation also takes place. So, here in the second figure you can see that these figures are taken from fluid mechanics by Munson. So, you can see that the second figure the separation is say separation point is here, and then you can see that even there is a possibility of a small wake formation even for this airfoil case. So, the same airfoil if you put it with a 0 angle of attack, then you can see that no separation takes place, but if the angle of attack is 5 degree, then there will be separation, and so depending upon the angle of attack, again the location of separation changes, and then also the boundary layer characteristics change. So, this case shows how the flow separation and then the streamline, the separation streamlines behave with respect to the placement of the body. So, this is the fifth case. So, now so we have seen that the flow separation, the boundary layer separation takes place, and it is very important to analyze from where the separation starts and what are the various characteristics with respect to the fluid flow parameters. It is very important in the analysis and in the design of various bodies wherever this boundary layer is forming, and then separation can take place. So, before discussing further the various application of the boundary layer separation, here you can see that a figure with respect to the for which here I have shown the variation of the velocity and the pressure. So, here this figure is taken from the book of fluid mechanics by A.K. Jain. So, let us consider the free stream flow over a curved surface like this. So, this is the curved surface and the free stream is coming like this. So, you can see that with respect to the surface a boundary layer will be formed, and then say initially say here at this location say approximately near to this point D, you can see that if you plot the velocity will be going like this, and then you can see that say this region of the where the boundary layer is formed, the pressure distribution, if you plot, you can see that the dp by dx will be negative, so dp by dx will be less than 0, and at this location if you plot the velocity gradient del u by del y at y is equal to 0, you can see that it will be, the gradient will be greater than 0, and if you take the second derivative of the velocity, you can see that del square u by del y square will be less than 0 at this location. And then you can see that due to the curvature of the surface here, a separation can occur at this location S. So before that, say for example at A, we can identify a section where the pressure will be minimum, the pressure P is minimum, and then you can see that at this location A, at this location, if you take the velocity gradient, so you can see that the velocity will be deforming like this, it is keep on reducing in like this case, and then the at A, at this location, you can see that the gradient of the velocity del u by del y will be greater than 0, and del square u by del y square will be almost 0 due to, since this pressure is P minimum. So here at this location it will be del square u by del y square will be 0. So that is at this section at A. And now if you consider a section at S where the separation already starts, so you can see that the separation streamline is here, so the velocity plot is here, so the velocity will be changing like this, and then if you plot the velocity gradient, you can see that del u by del y at y is equal to 0 will be 0 near A. So this location near A, or say at S, it will be, the velocity gradient will be becoming 0 at this location, and del square u by del y square will be also 0 at this location, and then the flow separation takes place, and then you can see that the pressure dp by dx is from here onwards, after this P minimum, the pressure minimum, the pressure gradient increases, dp by dx will be greater than 0 like this, and then near E, wherever after the separation takes place, you can see that del u by del y at y is equal to 0 will be less than 0, and del square u by del y square will be greater than 0, and then you can see that the velocity, if you plot, you can see that it is the reversal takes place, velocity reversal takes place after the separation of the streamline or the boundary layer separation. You can see that the velocity will be of this shape, and then here a wake will be formed. So here with respect to this figure, here we have analyzed, say with respect to the flow over a curved surface, how the velocity changes with respect to the boundary layer separation, say from starting and to after the separation takes place. Say initially the with respect to the boundary layer, the velocity pattern is different, and then the where the separation starts, the boundary layer separation starts, the velocity parameters, the velocity behavior is different with respect to section, and then after the separation you can see that reversal of the flow direction, there will be changes in direction of the velocity, and then we say that is why we say that a wake is formed. And then we have also seen how the pressure is changing. So the initially the pressure gradient is less than 0, and then there is a location where the pressure is minimum, and then the pressure gradient is dp by dx is greater than 0 after the separation starts. So this slide shows how the boundary layer separations and with respect to pressure distribution, how the parameters like the velocity, the gradient of velocity, and the second derivative of the velocity del square u by del y square is changing. So this way we can analyze various, say for various structures or for various blunt bodies or various surfaces, how the boundary layer separation takes place and how the pressure changes, how the velocity gradient changes. So now before going to the other topics like drag, let us see what are the application of this separation. So we have seen with respect to the shape of the body, with respect to whether it is a blunt body or with respect to whether it is a circular cylinder or whether it is a sphere or a curved surface, the boundary layer can separate at various locations and then a wake formation takes place. So I already mentioned there is a large number of applications of this boundary layer separation in, especially in the design of, say, aeroplanes and then space shuttle, and also the design of automobiles. So some of the applications of separation are listed here. So, the potential flow region, say with respect to the boundary layer separation, you can see that the potential flow region does not recombine at the rear end of the body. So, as we have already seen the various cases. So, this is because of the existence of the vortex field. So, we have seen that after the separation takes place, there is a possibility within the wake, there is a possibility of vortex field. So, that the potential flow region does not recombine at the rear end of the body. So, hence pressure at the rear end of the body is considerably lower than that is in the free flow region. So, the pressure changes at the rear end of the body is considerably lower than that is in the free flow region. So, after the boundary layer separation and then this wake formation, or due to the existence of the vortex field, what happens after the separation takes place. So, this principle we can utilize in the design of automobiles and also in the design as far of various flying machines like aeroplanes and other equipments. So, these are some of the important applications with respect to the separation of the boundary layer. So, here now in this slide, so now as I mentioned, there are a number of applications of this boundary layer formation and its separation. So, you can see that say the boundary layer separation, after its say identification of this boundary layer separation, its boundary layer formation and separations, we can see that this is very much used especially in the design of vehicles in automobile engineering. You can see that the shape of the cars also changed the last few decades. So, since you can see that wherever the separation, say for example, in this case here this car is concerned, here shape of car is plotted with respect to the boundary layer formation and the separation is plotted here. So, you can see that at this location the separation starts, and but here you can see this car is concerned, you can see at the rear end the separation starts. So, as we have already seen the case of airfoil, say if the airfoil is placed in such a way that angle of attack is 0, so that there can be a condition where no separation, so that the flow is much smoother. So, like this in the automobile industry also we can utilize this principle, so that there will be less resistance while driving the car or while driving the vehicle. There will be of course wind will be there, wind effect will be there on the vehicle. So, the design of the surface of the vehicle in such a way that the separation is taking at the rear end, and then there is the flow resistance will be much lesser, so that we can design. You can see that the shape of the cars, how the shape of the cars are evolved, say starting say earlier you can see that in 1960s and 50s their design was like this, and now you can see the latest design of the vehicles you can see here like this. So, there will be, especially say for the cases of sports cars, you can see that the shape is designed in such a way that the say separation takes place at the rear end, so that there will be much very less resistance to the movement with respect to the wind effect on the vehicle. So, similarly the design of buses, trucks, all these automobiles we can do in such a way that in the resistance with respect to the wind effect is much lesser on the vehicle which we consider, and then separation we can, if it is at the rear end, it will be much better as compared to the, if say in the case where the with respect to the vehicle. So, here the design, this study of the boundary layer separation and its analysis helps in the automobile design, deciding the shape, so that there will be less resistance to the with respect to the wind effect on the automobile. So, like this in a very similar way, when we design the shape of the aeroplane, its wings and its various components, we can utilize this boundary layer separation theories, and then so that we can design the aeroplane wings and other components such a way that there will be minimum resistance with respect to the wind on the aeroplane. So, like this there are number of applications we can find out this boundary layer formation and the separation of the boundary layer. So, further this say we have seen how the boundary layer forms, and then what are the governing equations, and then we have also seen the boundary layer separation and then its applications. So, now another important thing is, say with respect to the external flows are concerned, say flow over a body or a flow over a surface, two important parameters are drag and lift. So, now the next topic which we discuss is drag and lift effect. So, you can see that, say if you consider the flow over an airfoil like this what we were discussing earlier. So, you can see the wind or the free stream velocity is coming, and then you can see that there will be two important effects with respect to the flow over the body which is immersed in a fluid flow or the body which is moving through a fluid, and there are mainly two effects. One is called a drag effect and the second one is called a lift effect. So, with respect to this figure, it is, you can see that drag is in this direction of the flow and lift is in the normal to that. So, drag is the force exerted by the fluid on a body placed within the stream along the parallel direction of the flow. So, drag is defined as the force exerted, say as I mentioned here we are considering the external flows. So, where the body is immersed and fluid flow or the body is moving within the fluid. So, the drag is defined as the force exerted by the fluid on a body placed within the stream along the parallel direction, or the flow is taking place this direction. So, the body is the moving body or the body placed stationary, the body is with respect to the direction of flow, what is the force acting on the body. So, that force is called the drag. So, this is, we can see that this is very important aspect when we consider the design of many, say design of aeroplanes, design of submarines and many other equipments. And then the force exerted along the direction normal to the flow is known as lift. So, here the lift is indicated like this. So, what is the force acting along the direction normal to the flow is known as the lift. So, two important aspects, one is the drag, second one is the lift. So, as far as external flows are concerned or flow over a surface is concerned, or the movement of say some bodies within a fluid is concerned, two important aspects which we have to consider are drag and lift. So, it is already defined here, the drag and lift with respect to the slide, the figure here. So, we will be discussing in detail about this drag and lift effect. So, now some of the examples, as I mentioned, we can have a number of examples. Say the case of where the submarine is moving through the sea, we can see that the submarine is moving, then it is moving through the sea water. So, you can see there will be, of course, with respect to the movement of the submarine, there will be a drag effect which we have already defined, and also there will be lift effect. And then say a seabird moving through a fluid, you can see that how it is already plotted the streamlines and how the including the boundary layer, you can see here how it forms, and then there will be definitely a drag effect on the body surface of the bird, and then also there will be a lift effect. And also we can visualize this a person swimming in a swimming pool, you can see that with respect to the direction of the swimming there will be a drag force, and then also there will be lift force. So, we can have a number of examples, say with respect to the force exerted by wind on a flying aircraft. As I mentioned, there will be say this drag and lift are two important forces which we have to consider and we have to critically analyze with respect to the flying aircraft, how much drag will be there, how much will be the lift. So, these are two very important parameters which we have to consider, and also in the design of submarine and also many other, say also the force exerted on a free falling body, say like in the sedimentation process in a reservoir, we have to consider the drag and lift effects. So, some of the examples are shown here with respect to this slide here. So, now further to explain this drag and lift, let us consider say an aircraft like this. You can see that here in this slide, this aircraft is say moving this direction. So, you can see there will be drag and lift effect on this aircraft. So, the horizontal plane is like this and vertical plane is here. So, within the direction of the aircraft is moving this direction. So, with respect to that, wind will be coming on the aircraft, then you can see that drag will be in this direction, and then lift will be normal to that, lift will be in this direction, and then of course, the weight of the aircraft will be there, which we have to consider. So, weight of the aircraft W, and then drag force D, and then lift force in this direction. So, these are the forces which we have to consider with respect to the flying of this aircraft. So, it is the drag and lift effects are marked here in this figure. So, now we have seen the definition of drag and lift, and then we have seen various examples. So, we have to critically analyze this drag effect and lift effect on the bodies, so especially when we consider the external flows. So now, say we have already defined the drag in the direction of the fluid flow or the direction of the movement of the body or the vehicle or the body which we consider, and lift is normal to that. So with respect to this slide, here we can identify the drag and lift forces. So you can see that generally the drag and lift forces will be mainly due to the pressure, the normal stress variation or the pressure variation, and then with respect to the shear stress acting on the surface. So if we consider a small element within a body affected by drag and lift forces as shown in this slide, you can see that this is the body which we consider, and then the pressure is say P, and say if you consider an elemental area dA, then you can see that the pressure will be P into dA, and with respect to this angle is theta, so that we can see that in this direction it will be the pressure force will be P into dA sin theta, and the normal direction it will be P into dA cos theta. So similarly, if you consider the shear stress, so with respect to the viscous fluid, there will be shear stress will be there on the body. So if you consider the shear stress, you can see that this direction with respect to this angle theta, this direction shear force will be tau 0 dA cos theta, and this normal to that upward direction the shear force will be tau 0 dA sin theta, where tau 0 is the shear stress acting on this elemental area. So with respect to this, the pressure or the normal stress and the shear stress, we can derive the expression for the drag and lift. So with respect to this figure, so here we define on that elemental area which we consider, the lift force is equal to dFL is equal to tau 0 dA sin theta minus P dA cos theta. So this P dA cos theta in this direction and tau 0 dA sin theta in the opposite direction. So that is why we are considering with the negative sign here. So the lift force on the elemental area is equal to tau 0 dA sin theta minus P dA cos theta as written in this equation number 1, and then the next force is the drag force is concerned. You can see that both this force, the P dA sin theta and with respect to the shear stress, both are in the same direction. So we can write DFD, the drag force on the elemental area, DFD is equal to P dA sin theta plus tau 0 and dA cos theta as given in equation number 2. So these are the equations which we consider for the lift force and the drag force, for which we consider an elemental area, and then we consider the normal stress or the pressure force, and then the shear stress or the shear force, and then we have found with respect to the direction, with respect to the angle theta, we got two equations for the lift force on the elemental area and for the drag force on the elemental area as shown in equation number 1 and 2. So now to find out the total drag force or the area which we consider, we can just integrate with respect to the area, say for the two-dimensional case which we consider. So hence the drag force is concerned, we can just integrate. So this expression equation number 2 we can integrate. So hence the drag force is Fd is equal to integral P dA sin theta plus integral tau 0 dA cos theta with respect to area A. So this expression gives the equation for the drag force for the body which we consider. So similar way, the lift force is concerned, we can say now the elemental area dFL, we have seen the lift force on the elemental areas in equation number 1. So we can integrate this expression equation number 1, so that we get the lift force as FL is equal to integral over the area A tau 0 dA sin theta minus integral P dA cos theta over the area A as in equation number 4. So this equation gives the lift force for the body which we consider. So equation number 3 and 4 gives the equations for the drag force and the lift force for the case which we consider. So now regarding the lift force is concerned, you can see that generally for viscous fluid flow, the shear stress component of the lift force may be neglected as it is small compared to the pressure force. So depending upon the case, the exact equation is given by equation number 3 and 4 for drag force and lift force, but depending upon the case, say maybe some cases the shear stress component we can neglect, and some cases we can neglect the pressure force depending upon the problem. So generally So, if we neglect the shear stress component as far as lift force is concerned, then we get this lift force FL is equal to integral A P dA cos theta, it's minus, since we consider this equation here. So, this gives the lift force. So, as I mentioned, how we place the body. So, this the drag force and lift force effect can be different. Say for example, if I consider this, say now, say this as a body, let me consider a plate like this. So, now I am placing this plate here. So, this is the plate, and then you can see that the fluid flow is coming like this. Then you can see that as far as the drag force is concerned, here you can see that the shear stress effect will be much higher than the pressure force. So, in this case, if the body is placed like this, then we have to consider the shear stress component will be much larger. So, the drag force effect on this will be mainly with respect to the shearing effect. But if I place the same body in the other direction, you can see that there will be a pressure difference between this side and the other side, and then you can see that we have to consider the major component in this will be the pressure force. So, accordingly, in the equation which we consider, we have to see that whether the pressure drag is much higher, or the shear, the drag due to the shear effect is much higher. So, this drag condition with respect to the placement of the body, with respect to the body shape, it is some of these effects are plotted here. So, if we consider this flat plate, which we consider like this, say if you put in this location with respect to the free stream, then you can see that large wake will be formed, and then here the pressure effect will be much higher. So, this is in the case of a flat plate, and then as far as sphere is concerned, here the boundary layer formation and wake formation also shown, and then corresponding the drag effect will be varying. So, and if the same sphere is put in with a fairing like this, so that you can see that including the boundary layer separation changes, and then instead of the pressure effect, it will be more, the shear effect will be much higher, and then we have to consider in the equation correspondingly. And the same, the sphere is inside a housing like this, you can see that here, then you can see the boundary layer separation is at the end, and also drag effect will be mainly due to with respect to the shearing effect. So, like this, say the drag effect we have to say depends upon how we orient the body or how the body is moving. So, with respect to that, we have to consider whether the pressure effect, so as in this equation number 3, whether it is major component is pressure effect or the shear force or shear stress component, and accordingly similarly in the case of lift force also we have to consider. So, accordingly now say this drag is concerned, we have already seen the major components are due to the pressure and the pressure variation, and then with respect to shear stress or the viscous effect. So, now accordingly we can say classify the drag. First one is the pressure drag. So, the pressure drag is caused by the pressure difference between the front and rear of the body. As I mentioned, if the body is placed across the free stream velocity, then a pressure drag is created. So, the pressure drag is caused by the pressure difference between the front and rear of the body. So, here you can see a pressure drag is created. So, in equation 3 accordingly, the first integral term is called the pressure drag. So, FdP is equal to integral P dA sin theta. So, this depends on the form or shape of the object, as we have already seen here. So, hence sometimes we call this form drag. So, depending upon the shape of the body, the drag effect is changing. So, according to the shape, this can be varying. So, that is what is obvious. According to the shape, the drag effect will be different. So, this is some literature, this pressure drag is also called as form drag. So, this dominate in case of flow over a bluff body, as you can see here, this is the bluff body. So, the pressure drag is dominating. So, in the case of this here, this and here also the pressure drag will match, but when it is putting this way, the pressure drag reduces and the shear effect will be much larger. So, the pressure drag dominates in case of flow over a bluff body. So, here also another example is placed here, a person's in the swimming pool, pressure difference between the front and rear sides, therefore, pressure drag exists. So, between this side and the rear side there is a pressure drag. So, that we have to consider. And then the second one is the friction drag, as I mentioned. So, the drag can be mainly due to pressure drag and friction effect or the viscous effect. So, this friction drag, it exists due to the viscous effects of the fluid, and the second integral term is called the friction drag or the shear drag. So, FdF is equal to integral tau 0 dA cos theta over the area A. So, this depends on the extent and character of the boundary layer, as we have seen here in the last figure. So, this depends. So, here the friction drag will be much higher. So, it depends on the extent and character of the boundary layer. It is sometimes called as viscous drag. So, the entire friction drag is created within the boundary layer. So, like this we can have the pressure drag, and also we can have the friction drag. And so, here this is an example. So, for flow past an airfoil, the shear stress acting along the line of the body causes the friction drag. So, this shows the skin friction drag. So, here the friction effect will be, or the viscous effect will be much larger, and then we have the skin friction drag. So, like this, so depending upon the cases, we have to consider the pressure drag or the friction drag. And now in the next lecture we will be discussing more about the drag and its effects, and then with respect to the laminar boundary layer, or with respect to the turbulent case, how the drag we will be, how we will calculate the drag, and how the various parameters we have to consider with respect to the drag on the body we will discuss in the next lecture.